We are going to start now the next lecture, lecture 6 of chapter 1, class 12th mathematics, relations and functions. In this lecture, we will talk about binary operations. So to understand the definition of binary operation, we should understand the term the closure property. So suppose an operation is given to us, it is denoted like star. Operation means we are talking about as addition is the operation, multiplication is the operation, all these are the operation. So any general operation we are talking about, it is represented with star on a non-empty set S. This operation, it is defined applied on a non-empty, on the elements of the non-empty set S, and it is said to satisfy the closure property if we consider two elements A and B from the set S. Then A star B, this also belongs to S, and this thing holds for all A comma B belongs to S. Then we say that S is closed for this operation star, and the operation star on a non-empty set S satisfying the closure property is known as a binary operation. This definition will be more clear to you with the example. So first of all, we are talking about the set of natural numbers, and we are defining the binary operation as addition, A plus B. This is the operation we are talking about. This is the set S we are talking about. So to prove that this is a binary operation, it means that n is, we have to prove that n is closed for addition. So what we are going to do, we are saying if we take two elements from n, that is we are considering two natural numbers, then we know that A plus B is also a natural number, and this thing holds for all A, B belongs to n. So we are saying that addition on the set of natural number is a binary operation. Next we have is multiplication on n is a binary operation. So if we consider A comma B belongs to n, then we know that the product of two natural numbers is also a natural number, and this thing holds for all natural numbers. So we have mentioned this result over here, that addition and multiplication are binary operations on the set of integers, rational numbers, real numbers and complex numbers. As we have proved in this case, we can prove this result for the set of integers, for the set of rational numbers, real numbers and complex numbers, that is addition and multiplication. If I suppose replace this A with n with R, I am saying A plus B, this also belongs to R, and this thing holds for all real numbers A and B. It means that addition and multiplication operations, these are closed on the set of real numbers. So likewise we can prove this result for all these sets. Next, if we are talking about these operation of addition and multiplication on the set of irrational numbers, suppose we are talking about the set of irrational numbers, it is represented by S over here. So we consider two elements A and B from S, then we have to check whether A plus B and A star B, these belong to S for all A, B belong to S. Is this thing true? We have to check whether this thing is true or not. So we are saying, suppose we are considering an element 2 plus root 3, this belongs to S. We are considering another element 2 minus square root 3, this element also belongs to S. And if we are writing A plus B, or we are writing this element, we are saying this is A, this is the element B, A plus B will be 2 plus root 3 plus 2 minus root 3, this is equal to 4, and this is not an irrational number. So we are saying that addition on the set of irrational is not a binary operation. Similarly, if we are considering the element say root 2, this is a is equal to square root 2. We are considering say another element b is equal to minus square root 2. Then a into b, we are talking about the operation multiplication, that is equal to minus 2, and this is not again the irrational number. So we are saying that the multiplication on the set of irrational is not a binary operation. Next is let S be a non-empty set and PS be its power set. Next we have is let S be a non-empty set and P of S, it is the power set of S. Then the union operation on power set of S, we are saying it is a binary operation. We have to prove this thing that this is a binary operation. So we are considering two elements from power set of S. Power set means it is collection of all subsets of S. It means the elements of this power set, they are in the form of set. So we are considering that A belongs to power set of S and B belongs to power set of S. Then we are saying that A union B, this also belongs to power set of S for all A, B belongs to power set of S. And for the proof of this thing, you can refer to our videos related to the sets where we have proved these kind of results. Next we are saying intersection on PS is a binary operation. So again we are saying A belongs to power set of S, B belongs to power set of S, and this thing implies us that A intersection B, this belongs to power set of S for all A comma B belongs to power set of S. So intersection on power set of S is also a binary operation. So we are basically proving the closure property over here to prove that any operation, it is the binary operation. Now the next example we have, it is subtraction on the set of natural number is not a binary operation. So if we consider a number 3 belongs to n, now we have to prove that this is not a binary operation. It means we have to prove that this operation, this is not closed. So not closed means we have to show two natural numbers the answer of whose subtraction it is not a natural number. So the numbers we are choosing, they are 3 and 5, these belongs to n. But what we see is that 3 minus 5, that is equal to minus 2, this does not belong to n. So we are saying subtraction is not closed on natural numbers, or we are saying that this subtraction is not a binary operation on set of natural numbers. Next is subtraction on the set Z of integers is a binary operation, because if we consider two integers a and b, then we know that the difference of any two integers is always an integer. When we are talking about natural number, this number, this is not a natural number. But when we are talking about the difference of two integers, it is always an integer. Next is let n be the set of all natural numbers. Then the exponential operation, this a comma b is equal to a raised to the power b, is a binary operation on n. So we are saying if we consider any two natural numbers a comma b belongs to n, then we know that a raised to the power b, this is also a natural number. The power of any natural number is a natural number. So we are saying that this operation is also a binary operation. Next is let z be the set of all integers, then the exponential operation is not a binary operation. If we consider two numbers, say a is equal to 2 and b we are saying it is minus 3. So the answer we obtained for a raised to power b, it is 2 raised to power minus 3. This is equal to 1 by 8 and this is not an integer. So we are saying that this operation, this exponential operation, this is not a binary operation on the set of integers. Next, we have listed some properties of a binary operation. So first is the associative law. So a binary operation star on a set, we are given a non-empty set S, and a binary operation star is defined, and it is said to be associative if A star B star C. This is equal to A star B star C. So what this thing means is that first we are performing this operation A star B, and then we obtain some answer. It is a binary operation. It means this A star B, whatever answer we will obtain, that will be in S. We are saying again for S and this element A star B and C, we can apply this operation, and the answer we obtain, that will be in S, because this star operation, it is given to be a binary operation. And we are saying other way to solve this is that first we are performing the operation on B star C, B and C, and then whatever answer we are obtaining, that will belong to S. Then we are applying this A star into this element, and we obtain again the answer in the set S. Next is the commutative law. So a binary operation star on a non-empty set S is said to be commutative if A star B is equal to B star A for all A comma B belong to S. So this thing means that either we are solving A star B or B star A, the answer will be same. If this property holds, then we say that binary operation, it is commutative. Next is distributive law. We are saying if we have three elements A, B and C, and we have two binary operations star and this O, you can read it as O or off, and these are defined on a non-empty set S. We are talking about two operations now. Then we say that star is distributive over O if A star BOC, this is equal to A star B OA star C, and this thing holds for all ABC belongs to S. If this property holds, then we are saying that this operation, this binary operation, it is distributive. Next we have listed some problems related to these properties. So first we are saying let R be the set of the real numbers. Then we have already seen that the addition and multiplication, these two operations we are talking about, multiplication suppose we are representing with this dot, both these operations, they satisfy the closure property, because if we take two real numbers, I am talking about A star B, or star is any of these two operations, either it is addition or multiplication, then we know that if A comma B, this belongs to R, then A star B belongs to R, for star being these two operations. What this thing means is that A plus B belongs to R and A into B belongs to R. So this operation is closed under on R, or we are saying that closure property is hold. So this is a binary operation. Next is, if we are talking about the associative property, we know that for both these operations the associative property it holds. So it is either we calculate A plus B first, then add the answer to C, or we are calculating B plus C first and then adding the answer to A, we obtain the same answer. Similar result hold for A into B into C, that is equal to A into B into C. So we are saying that these operations, addition and multiplication, these are both these operations, these are associative. Similarly, when we are talking about A plus B, this is equal to B plus A, and A into B is equal to B into A. These properties is holds for all A, B, C belonging to set of real numbers. So we are saying, because these two results they hold, so we are saying that the real numbers they follow the commutative law. Next we have is multiplication is distributive over addition. So we are talking about this property that A into B plus C, that is equal to A into B plus A into C. This is multiplication distributes over addition, but addition is not distributive over multiplication. We are saying there is no such property like A plus B into C is equal to A plus B into A plus C. There is no such property that holds over here. So we are saying that this set of real numbers, when we are talking about, and we are talking about these two operations, addition and multiplication, so they are satisfying closure property, they are satisfying associative law, they are satisfying commutative law, and we have the multiplication distributes on addition. The next result we have is, this result we are talking about the set Z of all integers we are saying, then the subtraction on Z is a binary operation. But what we can see is, if we consider two integers, say one integer we are considering it is 3, second it is 5, then 3 minus 5, it is not equal to 5 minus 3. Second thing, 3 minus 4 minus 5 is not equal to 3 minus 4 minus 5. These properties we are talking about. So this thing shows us that this operation, it is neither commutative nor associative. Next is the binary operation star defined by a star b is equal to 2 times a plus b. We have to calculate the value of 2 star 3 star 4. So we are talking about, first we are calculating 2 star 3. The answer we have, it is 2 into 2 plus 3. This is equal to 7. Now we are calculating 7 star 4. The answer we have, it is 2 into 7 plus 4, that is equal to 18. So the final answer we obtain, it is equal to 18. Next is, if star is the binary operation on the set of integers defined by a star b is equal to this, we have to find 2 star 4. So 2 star 4 will be 2 plus 3 into 4 square. This is 2 plus 3 into 16, that is equal to 2 plus 48, that is equal to 50. Next we have is the identity element. This is the definition we have. So it is, let star be a binary operation on a non-empty set S. This is the identity element we are talking about, and it is given that star is a binary operation on S. An element E belongs to S if it exists such that A star E is equal to E star A is equal to A for all A belongs to S, then this E is called the identity element. So the examples are given over here. If we are talking about the operation addition and set, we are talking about it is R. We want to find, we are saying we consider a number A belongs to R. We want to find a number, the operation we are talking about it is addition. We are saying some number is there plus A should be equal to A, and this should be equal to A plus some that number. So we are saying in this case the identity element we have, it is 0, and this 0 belongs to R. There is a real number 0 for which 0 plus A is equal to A is equal to A plus 0. So this kind of number, this is called the identity element. When we are talking about the multiplication, then we consider some A belongs to R. We want to find a number which when multiplied with this number 0, then the answer we obtain is the same number. We are trying to find a number which when multiplied with A. Why we are multiplying over here? Because the operation we have now, it is multiplication. The answer we want, that should be equal to A into dash, that should be equal to the identity 1, the same element we are talking about A. It should give us the same element A. So in this case the answer we have, it is the number 1. We are saying there exists 1 belongs to R for which this thing holds for all A belongs to R. So we are saying 1 is the identity element in R. Next, suppose the power set of a set S is given to us, is non-empty set S is given, and P of S is the power set, and we want to find the identity element. The operation that is given to us, it is union operation. It means we are talking about the set A which belongs to power set of S. So we want to calculate a set for which this answer is equal to A and this is equal to that set union A, and we know that if we take the union of any set with the set phi, then the answer will be A. So we are saying that in this case this phi is the identity element. Next is the identity element for the intersection. So we are saying this again, we are considering this set A from the power set. It is A intersection some set should be equal to A, and that should be equal to that set intersection A. And we know that if we take the intersection of a set with the power set, the universal set we are talking about, the universal set in this case it is S. So we are saying if we take the intersection of a set A with the universal set, which in this case it is S. So we are saying A intersection S is equal to A is equal to S intersection A, and this thing holds for all A belongs to power set of A. Why I am again explaining this thing, that someone may think like this, that A intersection A that is equal to A intersection A. Then you can write that this A is the identity element. But what is the problem over here, that if in place of this A I will replace B, the answer will change. We are saying that we want to find an element over here for which this property holds for every element of the power set. So if we are writing this set S over here, in place of this A, if I am writing say B, the answer will become B, this will become B, and this thing will hold, that this S will be the identity element in this case. So we are saying that this set S is the identity element for intersection of on power set of S. The next definition we have, it is inverse of an element. So we are saying suppose star is a binary operation on a non-empty set S, then an element E is the identity element we are saying, and suppose the identity element it exists. E is the identity element means that if we consider the element A belongs to S, then E star A is equal to A star E, and this thing hold for all A belongs to S. Then this is the identity element. We are considering that the identity element it exists. Then we are saying A is invertible. We are considering an element A belongs to S. We are saying A is invertible if there exists an element B such that A star B is equal to B star A, that is equal to E. E is the identity element. This B is called the inverse of A, and we write A inverse is equal to B. So this thing will be more clear to you with this example. So we are saying suppose we consider the operation of addition on the set of integers, then we are talking about the additive identity, we know it is 0. Additive identity means if we consider any A belongs to Z, then A plus 0 is equal to A is equal to 0 plus A, and this thing holds for all A belongs to Z. Now we want to find the inverse element over here. So inverse means that we want to find an element, this should be equal to identity element we have, it is equal to 0, and this should be equal to dash plus A. So the answer we obtain, what we add to A to get 0, it is minus A. If A is an integer, then minus A is also an integer. This is equal to 0 and this is equal to minus A plus A. So this element minus A, this is the inverse element of A for this operation. Now if we consider the operation of multiplication on the set of integers, then we want to find the inverse element of this operation. So first of all, we are talking about the identity element. We are considering A belongs to Z. We want to find a number such that A into dash, that is equal to A, and that is equal to dash into A. The answer we have over here, it is 1. We are saying A to 1 is equal to A is equal to 1 into A. So this 1 is basically the identity element. Now when we want to find the inverse, the definition of inverse we have A star some element that should be equal to identity. that should be equal to some element into a. So that element we have over here, that is equal to 1 by a. Now if we consider say a is equal to 2, then this thing implies 1 by a is equal to 1 by 2, and this is not an integer. So it means for a is equal to 2, inverse does not exist. Now if we are taking a is equal to 1, then we have 1 into 1 is equal to 1 is equal to 1 into 1. So the inverse of element 1 is inverse of element 1 is 1. If we are talking about the number say minus 1, then we are saying minus 1 into minus 1, that will be equal to 1. So inverse of element minus 1 is minus 1, and except for these two numbers, the inverse does not exist for any other number. If we consider a is equal to say 7, then 1 by a will be 1 by 7, which is not an integer. So we are saying no integer other than 1 and minus 1 has inverse in multiplicative inverse in the set of integers z. Now the next question we have is, let z be the set of all integers, then addition on z is the operation given to us. Then we have for element a belongs to z and b belongs to z, we have a plus b belongs to z for all a comma b in z, that is the sum of two integers is always an integer. So we are saying it is satisfying the closure property. Next, a plus b plus c, that is equal to a plus b plus c. This property it is called the associative property. Next, a plus b is equal to b plus a, so it satisfies the commutative law. Next we have to find the additive identity. Additive identity means something plus a should be equal to a is equal to a plus something. So that element we have in this case it is 0. So 0 is the additive identity. Next we have to find the additive inverse. Additive inverse means something is there, some element is there plus a, that should be equal to the identity element. In this case it is 0, that is equal to a plus dash. Now the answer we obtain in this case it is minus of a. So we are saying the additive inverse we have, that is equal to minus a. Now the next question we have is, let R naught be the set of all non-zero real numbers. This is important to note over here that these are all non-zero real numbers, that is all real numbers except the number 0, and the operation that is given to us it is multiplication on R naught. So first of all we are proving that this is a closed operation or this is a binary operation. So for some a belongs to R naught and b belongs to R naught, we have a star b that belongs to R naught. This answer cannot be, this is a real number which cannot be 0 unless one of a or b is, unless one of means at least one of a or b is 0. So we are saying their product is also a non-zero real number. So this element, this belongs to R naught, and hence it satisfies the closure property. Next is associative law. So we are considering three elements a, b, c. They belong to R naught. We are saying a, b into c, that is equal to a into b, c. This property holds for all non-zero real numbers. So we are saying that this operation it satisfies associative law. Next, it also satisfies the commutative law, that is the multiplication for real numbers it is commutative. So for non-zero real numbers also it is commutative. Next we are talking about the existence of the multiplicative identity. So we want to find an element such that is equal to A is equal to A into that element, and we know that the element over here, that element we will have, it is 1. That is 1 is a non-zero real number which when multiplied with A gives us the answer as A. So 1 is the multiplicative identity, and this thing holds for all A belongs to R naught. Next is the multiplicative inverse. So to calculate the inverse, we are saying we are talking about an element A. We want to multiply it with something so that the answer is the multiplicative identity, that is A into dash. So the answer we have over here, it will be 1 by A. Now this 1 by A, it exists for all A belongs to R naught, because A is never equal to 0. So 1 by A will always exist. So we are saying that the multiplicative inverse of A is 1 by A. But suppose in place of R naught, in place of non-zero real numbers, if it is given real numbers, then multiplicative identity will not exist for 0, because 1 by 0 is not defined. So this thing is important to note over here, that we are talking about the non-zero real numbers. Next is this operation star is defined on the set of integers, that is set of integers, and it is defined like A star B is equal to A plus B plus 1. So if we consider two integers, we are talking about A star B, we are considering A comma B, this belongs to Z, then A star B is equal to A plus B plus 1, this will also be an integer. So we are saying that it satisfies the closure property, that is this operation star, it is closed, so it is a binary operation. Next we are talking about the associative law. So for associative law, we are considering A star B star C, so that will be equal to, first we are solving this value A star B. When we apply the formula on this term, the answer we obtain, it is A plus B plus 1 star C. This will be equal to A plus B plus 1 plus C plus 1. So the answer is A plus B plus C plus 2. Now if we are calculating the term A star B star C, the answer we obtain, it is A star B plus C plus 1. This is equal to A plus B plus C plus 1, and this is equal to A plus B plus C plus 2. So we obtain that A star B star C is equal to A star B star C. Next is we are talking about the, so this property, it means it satisfies the associative law. Next we are talking about the commutative law. If we calculate the value of A star B, that is equal to A plus B plus 1, that is equal to B plus A plus 1, that is equal to B star A for all A B belongs to the set Z. Next thing, we have to find the this identity element. So for identity element, we want to calculate an element, say element E is there, which is the identity element, then E star A should be equal to A, that should be equal to A star E. So we are saying we want to calculate this element E such that A, if we solve this, it is E plus A plus 1 is equal to A, that is equal to A plus E plus 1. Now we consider these two equations, the answer we obtain, that E is equal to minus 1. So we are saying if we substitute E is equal to minus 1, then this property is satisfied for all A belongs to Z. So minus 1 belongs to Z is the identity element for star. Next is existence of the inverse element. So let Z belongs to A belongs to Z, A is any integer, and we want to find an element such that A star that element. Suppose that element we are considering over here, it is B, and the answer should be equal to the identity element, that is equal to minus 1, and this should be equal to B star A. So when we apply the definition of this function over here, this is the definition of the function we are talking about. So we get A plus B plus 1 should be equal to minus 1 should be equal to b plus a plus 1. Both these equations, these are same. When we solve this equation, this first part we are talking about, we want to calculate this b, inverse element. So what we get is the value of b we obtain, that is equal to minus 2 minus a. So we are saying that for each a belongs to z, minus 2 plus a belongs to z is its inverse. This is important to note over here, that this element, this should belong to z for the existence of the inverse. Next is consider the operation star on q minus 1. Q is the set of rational numbers. We are saying we are talking about all rational numbers except 1, and the operation star, it is defined like a star b is equal to a plus b minus ab, and this is a and b, they belongs to q minus 1. So first of all we are talking about the closure property. So if we calculate a star b, the answer we are writing it is a plus b minus ab. So one thing is clear, that if a and b, these are the rational numbers except 1, then this number will be a rational number. Now suppose this value is equal to 0. So what we get is a minus b minus ab is equal to, suppose this value is equal to 1. We want to prove that this a star b, this is a rational number except 1. We suppose that it is equal to 1, then what we will get is that a minus 1, that is equal to, it is a b minus b, that is equal to b into a minus 1. Now we have this a comma b, they are rational numbers except 1. It means a is not equal to 1 and b is not equal to 1. But what this thing gives us, that b is equal to 1, and this is a contradiction. So we are saying this thing is not possible. It means whatever we have assumed, that a plus b minus ab is equal to 1, this is wrong, and thus we obtain that this, for a and b to be rational numbers except 1, we have a star b is equal to a rational number except 1. Next we have to prove the associative law. So we are considering the element a star b star c. So what is a star b? It is a plus b minus ab, and it is star c. So the answer we obtain, now this complete term we have, it is a, so it is a plus b minus ab, then it is plus, this term it is c, then it is minus a plus b minus ab into c. So when we solve this term, we will obtain it is a plus b plus c minus ab minus ac minus bc plus abc. Now if we solve the term a star b star c, the answer we obtain it is a star b plus c minus bc, and this is equal to a plus b plus c minus bc plus a into b plus c minus bc, and on solving this we will obtain that this is equal to this term. So what we obtain is that a star b and then its operation with c, or we are doing b star c and then we are this a star b star c, both these values, these are equal to each other. So we are saying it is satisfying the associative law. This star is associative. Next is commutative. So we are talking about a star b, that is equal to a plus b minus ab, that is equal to b plus a minus ba, and this is equal to b star a. So we are saying that this star operation is commutative. Now next we have to calculate the identity element and the inverse element. So for identity element we are saying, suppose some a is there which is a rational number except 1, and suppose e is the identity element which exists, then we have a star e should be equal to a, and that should be equal to e star a. So when we apply the definition of the function over here, we obtain that it is a plus e minus ae should be equal to a, that is equal to E plus A plus minus EA. If we solve this part, we obtain A, this A and A gets cancelled, so we are left with this E is equal E into 1 minus A is equal to 0. We know that A is not equal to 1 because A is the element of Q minus 1. So we obtain E is equal to 0. So it means for E is equal to 0, A into 0, A star 0 is equal to A is equal to 0 star A. This property we are talking about. So we get that 0 is the identity element for this operation. Next we have to find the inverse. So let B be the inverse. We are saying B belongs to Q minus 1. This is the inverse of the element A belonging to Q minus 1. Then we will have A star B that should be equal to identity element, and it is 0. So A star B means we are talking about it is A plus B minus AB is equal to 0. So this gives us A is equal to, if we shift these terms on this side, we get it is B into A minus 1, and we know that A is not equal to 0, so this implies us B is equal to A over A minus 1. So we are saying that the inverse element we have, that is A inverse, is equal to A over A minus 1, and this belongs to Q minus 1 because A is not equal to 0. Thus in each case we are saying for A belongs to Q minus 1, the inverse exists in Q minus 1. Now it is important to note over here that this element we are talking about, A over A minus 1, we are saying if this element is equal to 1, then what will happen? A is equal to A minus 1, we will get minus 1 is equal to 0. So this element, if we are saying suppose this element A over A minus 1 is equal to 1, first thing, it is not possible because A at A minus 1, these cannot be equal. Why we are saying so? How to prove this is, we are saying suppose it is equal to 1. If this is equal to 1, then we are getting the contradiction that minus 1 is equal to 0. It means this supposition is wrong. So we are saying that this A inverse, it belongs to the set Q minus 1. That is, it is a rational number, accept the number 1. Next is on the set of natural numbers, we define an operation star, and it is defined like for two elements m and n, two natural numbers m and n, m star n is equal to GCD, greatest common divisor of m and n. We have to prove that this operation star is commutative and associative. So commutative, we are saying if we consider the GCD of mn or we consider the GCD of nm, the answer will be same. So we are saying that m star n, that is equal to n star m for all m n and natural numbers. Next, when we are talking about the associativity, we are considering three elements m, n and p. Suppose these are the three natural numbers given to us. Then we are saying that the GCD of m comma n, this we obtain a number, and GCD of this number into p, that is equal to the GCD of the numbers m, n. We are talking about these two numbers over here, and this is equal to the GCD of m comma GCD of the number n and p. So this gives us, this is equal to, we are talking about this number GCD of this number, we are mean to say it is m comma n star p. This is the definition of GCD, and this is equal to m star n star p. And what is this term? It is m star n star p. So we are saying that this value is equal to m star n star p. So we are saying this operation star is associative on n. Next, we are given a set A. A has two elements, minus 1 and 1. And the operation given to us, it is a multiplication operation, and we have drawn the composition table over here. Composition means composition term means we are talking about this operation. It is called the composition operation. So this multiplication is given to us. We have listed all the elements of the set. What this table is representing, when we multiply 1 with 1, the answer we obtain it is 1. 1 with minus 1, the answer we obtain it is minus 1. Now when we multiply this minus 1 with 1, the answer we obtain it is minus 1, and this minus 1 into minus 1, the answer we obtain it is 1. So on performing this composition operation, the answers we are obtaining over here, these all answers, if I write the set over here, this is minus 1, 1 and 1, it means I am talking about minus 1 and 1, and this is equal to the set A. So it means all these elements, they belong to the set A. So we are saying it is satisfying the closure property because all the entries in the table are in A. Next property we are talking over here, it is the associative property. Now it is clear from here that A has only two elements, and when we are talking about the associative property, we require three elements. What is associative property? We have to write A, B and C. This belongs to A, but A has only two elements, so it is not feasible over here to talk about the associative law in this particular case. So we come to the commutative law. So if we look at the elements over here, if suppose I am talking about the multiplication of 1 with 1, this will give us the answer 1. Now I am talking about these multiplication, 1 into minus 1, that is equal to minus 1 into 1, 1 into 1, that is equal to 1 into 1, and minus 1 into minus 1, that is equal to again minus 1 into minus 1. So we are saying that this satisfies the commutative law, that is A star B is equal to B star A for all A comma B in the set A. This thing can also be seen in this way, that every row of this table coincide with the column. When we have to check whether this operation is commutative or not using the table, we are saying this row, it is 1 and minus 1, it coincides with this column, it is 1 and minus 1. The next row is minus 1 and 1, and it coincides with this row minus 1 and 1. So this is the process of checking commutative law when the composition operations are given to us. Next is the existence of identity element. So existence of identity means if we consider an element A belongs to A, we want to find A star or multiply dash is equal to A, that should be equal to dash into A. The element we will have over here, look at the answer over here, we want the same answer. If we fix this element 1, the answer we are getting it is 1. If we fix this element minus 1, the answer we are getting it is minus 1. I am talking about, look at this first row over here, it is 1 and minus 1. We are saying corresponding to this element 1, these two elements, these are 1 and minus 1. So we are saying A into 1, that is equal to A is equal to 1 into A. It means 1 is the identity element in A. Last we are talking about it is inverse. So if we look at this table again, we are saying look at this value 1, the identity element it is A. So we are talking about A star B should be equal to 1, should be equal to B star A. If I am talking about the element 1, I want to calculate something so that the answer is 1. If I am talking about the element minus 1, I want to multiply it with something so that the answer is 1. So what we are getting is 1 into 1 is 1, minus 1 into minus 1 is 1. So it means the inverse of 1 is 1 and the inverse of minus 1 is minus 1. Now next, the set A is given to us and the operation is defined like this. It is A operation B, A composition B, we are saying it is minimum of A and B. So the elements we are listing over here, it is 1, 2, 3, 4 and 5. 1, 2, 3, 4 and 5. So when I am talking about these first two elements, the minimum of these two is 1. Then I am talking about 1 and 2, the minimum is 1. 1 and 3, the minimum is 1. 1 and 4 minimum is 1, 1 and 5 minimum is 1. Next, for 2 and 1 the minimum is 1, for 2 and 2 minimum is 2. Answer is 2, 2 and 2. Similarly, the next answer will be 1, 2, 3, 3, 3. Next answer will be, this element is 1, 2, 3, 4, 4. And the last answer will be 1, 2, 3, 4 and 5. Now we are talking about the closure property and the commutative law. For closure property, we can see that all these answers in this table, they belong to this set A. All these answers, they belong to this set A. So it means these are this operation, it is closed. Second, we are talking about the commutative law. So for commutative law, look at this first row over here. This coincides with the first column. This second row, this coincides with the second column. This third row, this coincides with the third column. This fourth row, this coincides with the fourth column. And this fifth row, this coincides with the fifth column. So we are saying that this operation, it is a commutative operation. Similarly, we can draw the composition table for the maximum values of A and B. It is shown on our next slide. So we are, this set A is given 1, 2, 3, 4, 5. We have listed these elements over here, these elements over here. Now again, all the answers over here, they belong to the set A. So it is closed. Next, this first column, first row, they are same. This second column, this second row, they are same. This third column, this third row, they are same. This fourth column, this fourth row, they are same. Similarly, this fifth column and fifth row, they are same. So it means this operation is also commutative. Next we have is, let A star B is equal to A LCM of A and B. We have to find the identity element in N, the set that is given to us, it is N, and find all invertible elements in N. So identity element means we want to find A star something, so that the answer is A, and that is equal to something dash A. Now suppose that element, it is E. So we are saying it is LCM of A and E should be equal to A. And this thing is only possible when E is equal to 1. And this thing should hold for all A belongs to the set of natural numbers. And this thing is only possible if we consider E is equal to 1. We are saying the LCM of any number A with the element 1, that will be equal to A. So 1 is the identity element in 1. Next is, we have to find the inverse. So for inverse, we are saying A star something should be equal to the identity element we have over here. Now it is 1, and that should be equal to dash star A. It means we are saying that if suppose this element is B, then it means LCM of A and B should be equal to 1. And from this, what we get is, this thing is possible only when A is comma B, both these values, these are equal to 1. So what we mean to say from this is that it is not always possible to find the number B such that A star B is equal to 1, equal to B star A, but this thing is only possible if we consider the element A is equal to 1. So we are saying 1 is the only invertible element under this operation in N. I am again repeating this thing, that whenever we are saying that LCM of A comma E is equal to A, we are saying this thing should hold for all A. We want to find an element E, for with this hold for all A. Again in this case, if I am talking about LCM of A and A, it is A. If suppose I am talking about LCM, the number A I am considering, say it is 12. We know that the LCM of 12 and 2, it is 12. LCM of 12 and 3, it is 12. LCM of 12 and 4, it is 12. Then this thing doesn't mean that this 2, 3, 4, all these values, these are the identity elements. Identity element means we are saying LCM of 12 and 1, it is 12. LCM of 13 and 1, it is 13. LCM of 14 and 1, it is 14. So we are saying if we consider any element from this set of natural number, we take its LCM with 1, we get the answer, the same answer. So that is why we are saying this 1 is the identity element. The next question we have is, show that star operation on R minus minus 1 defined by A star B is equal to A over B minus 1, B plus 1 is neither commutative nor associative. So to prove the commutative law, suppose we are considering A is equal to 2 and B is equal to 3. So we get 2 star 3, that is equal to 2 over 3 plus 1, that is equal to 2 over 4, that is equal to 1 by 2. Now if we are calculating 3 cross 2, the answer we are obtaining is 3 over 2 plus 1, so it is 3 over 3, that is equal to 1. Clearly both these values, these are not equal to each other. So we are saying that this operation, it is not commutative. Next we have to prove that it is not associative. So we continue from this term. Suppose we are calculating, it is 2 star 3 star 1. The answer we obtain, it is 2 star 3. 2 star 3 value we have obtained, it is 1 by 2. We have to do the operation star 1. So the answer we obtain in this case, that is equal to, it is A, it is 1 by 2 divided by B plus 1 is 1 plus 1. So the answer we are obtaining, it is 1 by 4. Now if we are calculating 2 star 3 star 1, it is 2 star 3 star 1 means we are saying 3 over 1 plus 1. This value is 3 by 2. So the answer we obtain, it is 2 over 1 plus 3 by 2. So this is equal to 2 over 5 by 2, that is equal to 4 by 5. Again both these values, these are not equal to each other. So we are saying that 2 star 3 star 1 is not equal to 2 star 3 star 1. That is this operation, it is not an associative operation. Next is for all A, B belonging to N, we define the operation A star B, that is equal to A cube plus B cube. We have to show that star is commutative but not associative. So for commutative we are saying A star B is equal to A cube plus B cube, that is equal to B cube plus A cube. A and B, these are the natural numbers, so these A cube and B cube are also natural numbers. So we are saying that is equal to B star A. So this thing proves that this operation is commutative. Next we have to prove that it is not associative. So we are considering the element 1 star 2 star 3, and once we are considering 1 star 2 star 3. The answer in this case, it will be 1 cube plus 2 cube star 3. So this is equal to 1 plus 8 into 3, that is equal to 9 star 3. 9 star 3 means it is 9 cube. The answer we obtain over here, it is 9 cube plus 3 cube, that is equal to 756. Next, when we are calculating this term, we are getting it is 1 star 2 cube plus 3 cube. This is 1 star 2 cube is 8, 3 cube is 27. So this is equal to 1 star 35. This is equal to 1 cube plus 35 cube, and clearly these two values, these are not equal to each other. So hence we have proved that this operation, it is not an associative operation. Next is a binary operation star on the set 0, 1, 2, 3, 4, 5. It is defined as A star B, that is equal to A plus B if A plus B is less than 6, and this is equal to A plus B minus 6 if A plus B is greater than equal to 6. We have to show that 0 is the identity for this operation, and each element in A has inverse 6 minus A. So to prove that 0 is the identity, we are talking about A star 0, that is equal to A plus B. A plus B means the value of B over here, it is 0, and that is equal to A, because the value of A, it is always less than 6. We are saying the value of A can attain, it is 0, 1, 2, 3, 4, 5 and 6. A can attain one of these 5, not 6 is not included over here. We are saying that A can take the values from this set. So A is always less than 6. So A star 0, that will be equal to A, that is equal to 0 star A. So we have proved that 0 is the identity element. Next is each element A has the inverse 6 minus A. So if we take A star 6 minus A, the answer we will have, that is equal to, we are saying this is A and this is 6 minus A. So sum of both these values, it is A plus 6 minus A, that is equal to 6. It means that this value, it is A plus 6 minus A, it is not less than 6. So the answer in this case, that will be A plus 6 minus A minus 6, and this is equal to A plus 6 minus A minus 6, that is equal to 0, and 0 is the identity element that we have. So we are saying that A star 6 minus A, that is equal to A plus 6 minus A is equal to 0, and the inverse of A is 6 minus A. Next is let Q naught be the set of all non-zero rational numbers. So these are all rational numbers except 0. Star is the binary operation on Q defined by A star B is equal to AB by 4. We have to prove that this star operation, it is commutative, associative. We have to find the identity and the inverse element of A in Q. So first of all, we are talking about the commutativity. So we are saying A star B, that is equal to AB by 4, that is equal to BA by 4, that is equal to B star A. It means this operation, it is a commutative operation. Next we are talking about three elements A, B, C, they belongs to Q minus 0. Then A star B star C, that is equal to AB by 4 star C, that is equal to ABC by 16. Similarly, when we are calculating A star B star C, this is equal to A star BC by 4 and this is equal to ABC by 16. Both these answers, these are equal. So we are saying that this operation we have, it is an associative operation. Next we have to find the identity element. So to calculate identity element, we are considering an element A. We want to find an element E such that their product is equal to A. So we are saying A E over 4 should be equal to A. So this gives us E is equal to, when we solve this value, we are getting this implies E is equal to, this A and A gets cancelled because it is already given that A is not equal to 0. We are saying A belongs to Q naught. This implies A is not equal to 0. So we can cancel both these A. So we are saying E is equal to 4. So what we get is that E is equal to 4 means that 4 is the identity element in Q naught. The last part, we have to find the inverse of an element A in Q naught. So to find the inverse of an element A, suppose we are saying the inverse is B, answer should be equal to 4. A star B means it is AB by 4 is equal to 4. This implies the value of B is 16 by A. Clearly we have A is not equal to 0. It means this belongs to the set Q naught. So we are saying that each element A in Q naught has the inverse 16 by A. Next is let A is equal to n cross n. Now the elements of A, they are of the form A comma B, where A and B, these are the natural numbers, so they are in the form of ordered pairs, and star is the binary operation defined like A star B, AB, this ordered pair AB star C D is equal to A plus C comma B plus D. We have to show that A is closed for star. Closed for star means we are talking about A comma B star C comma D. This is equal to A plus C comma B plus D. If A and C are natural number, B and D are natural number, then this A plus C and this B plus D, both these numbers, these are the natural numbers. So it means this, both these elements, these are natural number, means this belongs to n cross n, and this thing proves that this operation, it is closed. Next we have to prove that it is commutative. So to prove that it is commutative, we are writing A comma B star C comma D, that is equal to A plus C comma B plus D. This is equal to C plus A comma D plus B. This is equal to C comma D star A comma B. So this thing proves that this operation is commutative. Next we have to prove that this is associative. So we are writing A star B star C. It is not star over here, it should be A comma B star C comma D star E comma F. We have put bracket over here. The answer we obtain, it is A plus C comma B plus D star E comma F. This is equal to A plus C plus E comma B plus D plus F, and we can write this is equal to A comma B star C plus E comma D plus F. This is equal to A comma B star, we have bracket over here, it is C comma D star E comma F, and this thing proves that this operation, it is an associative operation. Next we have to prove that identity element does not exist in A. So suppose we are saying there is an element which is the identity element in A. So what we will have, it is A comma B star, some element E will be there, this E will be of some form C comma D, such that the answer is A comma B. Now look at this term over here. We are saying we require this C and D to be the natural numbers. So for this thing to hold, if we open these brackets by this formula, we will get A plus C comma B plus D, that is equal to A comma D. So this thing implies us A plus C is equal to A and B plus D is equal to B. So this gives us C is equal to 0 and D is equal to 0, and this thing is not possible because C and D, these are the natural numbers. So we are saying that we cannot find the identity, there does not exist any element for which A star A comma B star is equal to A comma B. So we are saying that identity element does not exist in A. Now the next question we have is the set of fourth root of unity are given. So this set is -1, 1, iota and minus iota, and the operation given to us, it is the multiplication operation. We have to prepare the composition table. So this composition table, it is shown over here. These are the values 1 minus 1 iota and minus iota. These are the values 1 minus 1 iota and minus iota. We have multiplied these terms. 1 into 1 it is 1, then 1 into minus 1 it is 1. Suppose I am talking about this term iota. Iota into minus iota will be 1. So likewise we have multiplied all these terms. It is minus iota into minus iota will be minus 1. So this is the composition table that we have obtained we have to prove that A is closed for multiplication. So look at all these values over here. These values, these are from the set. These are all values, we are saying the answers we are obtaining. These are from the set A. So we are saying that this operation A is closed for multiplication. Next is we have to prove that it is associative. We know that the multiplication it is associative on A. Why? Because multiplication, when we are talking about the associativity in case of complex numbers, we have complex numbers, they are associative under multiplication. So these all numbers, these are complex numbers, so we can deduce from that these, for this set A, the operation multiplication will be associative. Next we are talking about the commutativity. So to prove that it is commutative, we are saying look at this first column over here. It is 1 minus 1 iota and minus iota. Look at this first row over here, both are same. This second column, second row, they are same. Next, this third row and this third column, they are same. Similarly, the fourth row and fourth column, they are same. So we are saying, from this we are saying that multiplication is commutative on A. Next is 1 is the multiplicative identity. We have to prove that 1 is the multiplicative identity. So from this table, we are I'm again drawing this table over here. I am talking about this element is 1 minus 1 iota and minus iota. This is 1 minus 1 iota and minus iota. Then we are talking about the multiplicative identity. It means I am talking about what number I will multiply with 1 so that the answer I obtain it is 1. I am interested in this number 1 over here. For minus 1, I am locating the number minus 1 I am getting over here. For iota, the number iota I am getting over here. For minus 1, the number for minus iota I am getting the number minus iota over here. So we are saying when we are multiplying these terms with 1, we are getting the same answers over here. So the multiplicative identity we have, it is 1, because these values, these are same over here, that whenever we multiply 1 with 1 we are getting 1, minus 1 with 1 we are getting minus 1. These are the same answers we are obtaining on multiplying with 1, that is A star 1, that is equal to A. Next is every element in A has its multiplicative inverse. So when we are talking about multiplicative inverse, the multiplicative identity we have, it is 1. So corresponding to 1, the inverse is 1. Corresponding to this minus 1, we have to locate minus 1 over here. We have minus 1 into minus 1, that is equal to 1. I am talking about this term over here, it is 1. Then iota into minus iota, this term it is minus iota. This is not minus 1, this is minus iota over here. We are saying minus iota into minus iota, it is 1. This is iota into minus iota. The answer we are obtaining, it is 1. Next is minus 1 into this term, it is minus iota into iota. We have the answer, it is 1. So we have 1 over at these places. This is basically the identity element we are talking about. So it means what we get is that the inverse corresponding to 1, it is 1. The inverse corresponding to minus 1, it is minus 1. Inverse corresponding to iota, it is minus iota, and inverse corresponding to minus iota, it is iota. This value we are looking at. So we are saying that every element in A has its multiplicative inverse.